In this lecture, we're going to look at some variable considerations, such as scope, value versus reference variables, and then the special case of dealing with strings. As we work through this lecture, we're going to be looking at some sketches of memory, and I'm going to be drawing this memory as a series of cells, and those cells are going to contain a value within them. As we run our program, all the variables are stored within the memory as it executes. There are different names for different parts of memory. You may hear heap and stack. This will make a little bit more sense as we work our way through our lecture and as we talk about method invocation next week. So I'm going to go ahead and get started in talking about scope. Simple definition of scope is just the set of statements a variable is visible and accessible within our program. And so we've already seen this when we have class data members versus local variables of a method. If I look at an example here we have this class scope world, private int value. This is a data member of the class. So this value data member is going to be accessible within each one of the methods within my class. So I can access it within method 1, with method 2, and any other methods that I may have. Now within this class, I have declared some methods. So here I have method 1, and here I have some local variables as method. I have integer x, integer val. Now x is only accessible within this method because it was declared within this block here. Now when I say int val here, this ends up being a different value than this value that was a data member of the class. So that's then where we use the scope resolution operator of saying this dot to say the value that I'm referencing here is actually the data member when I say this dot. Or if I just say value here, it's going to check to see if it is going to use the local definition. Now if I don't have a local definition and I use the word value, it's going to come up and then use the data member variable. Here's another example. This here x is going to be a different x than in method 1, and also know that our parameters are local variables of our method. So scope is just the set of statements that our variable is visible within our program. Here's another example. I have a single method here, integer a. A is accessible within method 1 and method 1 only. Now here I have an if statement and it has a block. Within any block we can declare our own variables. So I say integer b equals a times 6. B is accessible anywhere within this if block. But once we exit the if block, it has gone out of scope, so b is no longer accessible. So if we try to do manipulation with b down here, we're going to actually get a compilation there because it's out of scope and we can't access that. Now as we talk about variables in memory, there's two different types of variables that we will be using. We have value variables and reference variables. With value variables, the actual value of the variable is stored in the memory location. With reference variables, what it does is it stores a memory address which points to another location where it is referencing is stored. These two definitions will make a little bit more sense as we continue to work our way through this lecture. So let's look at an example of value variables. All our primitive data types are value variables. So here I've got int x equals 3, double y equals 5.2. So over here in my memory, I have a memory slot or memory cell for x and y. When this statement executes, it creates a memory cell for x and it puts the value 3 in there. And of course that value is going to be stored as a sequence of bytes, and that the bit pattern in those bytes are going to represent the value 3. And then for double y equals 5.2 out in memory, there's going to be a slot for y and it's going to put the value 5.2 there. Now what happens when we then copy primitive values is it actually copies the actual value. So here's our same example. We have x equals 3, y equals 5.2. Those values are stored out here in our memory. When I say integer z equals x, what it does is it goes over to x and actually makes a copy of that value and writes that same value within that memory cell. So now both z has 3 in it and x has 3 in it. Now if I go in here and set x to another value, let's say I had the statement here, x equals 5 at this particular point. What that is going to do then is it's going to come here to x and put the value 5 there, but it doesn't do anything to the value z, even though they both have the same value in there, because x only refers to its particular memory cell there. Now with reference variables, first thing to note, all object variables are reference variables. So that means anything that you instantiate with the new operator is an object variable, and what that's assigned to becomes a reference variable. So the variable in memory stores the reference, or our location memory, where the object that it refers to is actually stored. So let's look at an example here. Here we have a primitive variable, integer x equals 3, so we come down here to x's memory slot, and it has the value 3 in there. Now I say student s, so it creates a memory slot for that. When I say s equals new student, what that does is it goes out on the heap. All our objects are stored on the heap, creates a new student object. When it does that, it returns the memory address of that, and it writes that within s's memory cell. So then we can say s points to the location where that student object is stored. In other words, it refers you to where you need to go to actually find that particular student object. That's why it's called a reference variable. Now, when we copy reference variables, we're actually copying the reference. So we end up creating an alias for the same object. In other words, we have two different variables, or we could even have more than two different variables that refer to the same object. So if we look at this example here, we have x equals 3. Remember, that's the value variable, so it's just going to put 3 there. Student s, when I say s equals new student, it comes out here, makes my new student object on the heap, and then s now points to or refers to the memory location where the student object was allocated. Then when I say s2 equals s, what happens, that memory address gets copied here into S2, so the S2 now points to the exact same object. So S and S2 both refer to the same object now because we copied that reference value. Now we have to take note of this when we are now updating an object that's referred to by multiple reference variables. What's going to happen here? So I have this situation here. I have student s. So here's my memory slot for that. I say s equals new student. What that does then is it makes my new student object. Now s points to the memory location on the heap where the student object was created. Then I say student s2. So at that point it makes an s2 memory slot equals s. So it copies the value stored here, which is a reference value, from S up to S2. So then now S2 points to that same particular object. So at this point, if I say system.out.println s get first name, this is going to print out John. So it came in here, we say, let's say, when we created this, we initialized it with John, so it prints out John because it comes up to this object and says, what's your name? Well, it's John. Now when I say S2 set first name, notice here S2 comes up, it points to the same object and it says, now your name is Paul. So when we come down here, system.out.println, notice here we're going to reference by S again. It says S first name. S, we come up here, what's your first name? Oh, well, it is now Paul. So with reference variables, whatever alias I use to access that is going to affect all my aliases because it's going up and working on that object that's stored on the heap. Now, one other item I want to mention when we start working with objects is the word garbage. Garbage occurs when there's no longer a reference variable referring to an object in memory. So we have a situation here, student s equals new student. So we have our memory location s. We run new student, it goes out here and makes a new student object. S points to that at this particular time. Now student S2 equals new student. At this point it makes a new student object called John Doe on the heap, and S2 points to that object. Now when I say S2 equals S, so that means I'm going to take the address here and copy it up into S2 at that particular time, then S2 points to this particular student object. Notice now that there are no variables referring to this student object here. At that point, this object has become garbage. That means there's no way that we can access it, and it's taking up memory. So as our program executes, if we start to run out of heap space, Java will occasionally run what we call garbage collection and go through the heap and find all unreferenced objects, and note that that memory is now free to be used by other objects when we instantiate them. Now, when I say S2 equals null, what that is doing is it's saying come in here and put null in here. In other words, I'm not pointing to anything, so when I execute that statement, null is going to be written here, which would just be a series of zeros, and it no longer points to the student object. But just because I say S2 equals null here doesn't mean that that became garbage, because in this instance, S still points to that same student object. So this object is not garbage yet because we still have a variable that refers to it. Now I want to start discussing passing variables to a method. Remember, local variables of a method are placed on the stack, and each local variable is given a memory location on the stack in our slots there. And for primitive variables, the actual value is copied to the memory location, and for objects, the reference of that object is copied. So let's look at a couple examples here. Here's what we call a pass by value example, which happens with all our value variables. So here is our first method. Now, I didn't put animation into this particular slide, but we have called public void determine value. When we call this particular method, what happens is out on the stack, and the stack grows upward, it reserves a memory slot for Z and for val. As we execute this code, we say Z equals 3, so it comes out here and writes the value 3 in there. And then integer val equals, but can't do the assignment, it calls this calc method up here, where we're passing in the Z variable, which holds the value 3. So when I have this particular variable here, when I call calc, what it goes out to the top of the stack, it creates memory slots for each one of my local variables. So it creates one for my integer x, it creates one for my integer y. Now, when it's passed in here, Z is passed in, so it copies the value 3 into X's slot there. Then we execute the code and we say X equals X times 2. What's going to happen at that particular stage is this is going to become 6. And then when we say integer Y equals 100 minus X, well, the X it's referring to here has the value 6 in it, so 100 minus that equals 94, and then it's going to return that value. When it returns, it actually pops these two memory cells off the top of the stack, and now the stack pointer is going to point here. It always points to the top of the stack. It's going to return the value 94, and when it does that, it's going to put 94 in this particular memory slot. Now the next example I want to show is how pass by reference differs from pass by value. And pass by reference is going to occur whenever we are working with reference variables. In other words, whenever we're passing object variables around. So I have two methods here, create student and update student. We're going to call create student first. Please note, it doesn't matter what order these are within your Java file. It matters what order that they're called on how they appear on the stack. So let's, for sake of this illustration, we have called create student. At that particular point, it puts S1 on the stack. We say S1 equals new student. It has now created a new student object out on the heap, and S1 points to that particular student object. So when I say S1 set first and last name, it puts John Doe out here. So when I say system.out.println S1.get first name, it goes out here and it says, what's your name? Well, your name is John, so it prints out John. Now when I call update student, it comes out here on the stack, reserves memory slots for the local variables of that. So one of the local variables here is student, or STU, so it puts student in there. And now what did we pass in? We passed in S1, so it copies that value there, which is a reference variable. So now STU refers to that same student object. STU, even though it's a local variable method, is an alias for the student object. So now when I say STU set first name to Paul, it comes out here and says your name is Paul. It then returns back up here. This is popped off the stack. That pointer disappears. The top of our stack pointer is right here. And now when I say S1 get first name, it comes here and it says S1. What's your name? It's Paul. So notice here when we work with reference variables, if we change the object within the method that we're calling, it's going to change that object, and that's going to be reflected back in our method that called it. That's what's known as a side effect. The method we called has made a change to the state of our program, and that's reflected when you return. So that's called, again, a side effect. Pass by value versus pass by reference. A couple items to note on this. All primitive variables are passed by value. So that means your ints, your doubles, your bools, they're all passed by value. All reference variables, that means anything you instantiate with a new operator, are passed by reference. Again, as I mentioned before, be aware you can have side effects when you do a pass by reference. So is there a benefit to pass by reference? The reason that we do that is that when we come back here, when we make an object, these objects usually are fairly large and they take up a significant amount of memory. So if I ended up not passing them by reference, but actually placing those objects on the stack, my stack memory is going to get filled up very quickly if I'm passing a lot of objects in between my various methods. So the benefit and the reason that we have objects be stored on the heap and use reference variables for them is that we're going to save memory on our stack. It's going to save time also, as it's expensive to copy values over onto our stack. What happens if we, within a method, allocate a new object? So I'm going to just step through this one. I'm going to need you to sort of visualize in this particular example. So here's our method, what do I do? I've got my grade, which is of type grade, which is now a reference variable because this is an object that we're allocating. So out here on the heap, we've allocated a new grade object, and my grade now points to that. So when I print out my grade, it goes out to the reference variable, gets to the heap location, says what's your grade? It's 99, it prints out 99. When I call update grade, okay, this is a reference variable. We say passing in the grade, grade.setGrade 45. It goes out on the heap. It says, oh, your new value is 45. So what happens here then is when it returns, it's going to print out 45. Now we have create grade object. Notice here we're passing in the migrate object, which out on the heap it has the value 45 in it. We come down here, we've passed it in. This local variable refers to that same location on the heap. Now when I say grade equals new grade, what this does is it makes a whole new object. So my local variable grade reference variable here no longer is going to point to that grade object that has 45 in it. It makes a whole new object on the heap, and grade now points to that. So when I return, this gets popped off the stack, and no change has been made to the migrate object because when we worked on this one, we made an entire new object that we're working on. So at this point, when I say print out my grade, it's still going to say 45. It's not going to say 88 because this ended up creating a whole new object. So we've got to be careful when we're making new objects within a method. So what would happen if we actually needed that object back here is that we would then need to return that object by adding a return statement and say return grade. So returning values from a method, to return a primitive value from a method, we must use a return statement. To return objects, if we happen to make a new object within the method that we called, then we're going to have a return statement to return that reference variable, which will return a pointer to that object. However, if we just pass in an object, we can then change its state by just calling the appropriate methods there. Okay, how do we know if a variable is a value variable or a reference variable? All reference variables are allocated with the new operator. So when I say grade, my grade equals new, I know that it is a reference variable. All array lists, remember we're using the word new there, they are reference variables. Next week we're going to talk about arrays, and those are also reference variables. The last thing I want to touch base on are strings. And strings are sort of a special case on how we use them. Is a string a value variable or a reference variable? A value type or a reference type? All strings are objects. So anything that's an actual object means that it is a reference variable. So at any time you say my string equals, well, here we have new string, so it is making a new string object, and my string is now referring to that particular object. Now we have to ask yourself, why do I use dot equals instead of equal equal when I'm comparing the contents of two strings? So I've got a couple of examples here. Let's say I had the code where I make S and I make a new GIL object. So now S comes out here and makes a new GIL object on the heap, and S points to that. S2, with that I've made a new jack object. S2 then points to that object. When I say equal equal, what that is doing is actually going to these two cells, S2 and S, and is seeing, is the value here the same as the value here? Well, since they're pointing to different memory addresses, that's going to return false. So when you are doing equal equal, you are just checking to see if the actual reference variables themselves are equal. You're not doing any comparison with the objects that they're referred to. So if we need to compare strings, what we actually do is we say dot equals. So that means that we then go look at the objects that we're referring to, and then look at their contents to see if their first name strings are equal. So we must take care when we're comparing objects that we don't want to use equal equal, because that's just going to see if the two reference variables are pointing to the same object. If we want to look at the contents of the object and compare those, we're going to have to use the dot equals. Now, if we write our own classes, what we're going to have to do is override the dot equals so we can specify what is actually going to be compared within those objects. Now, I mentioned strings are special. Because we use strings so often, there are some shortcuts available that we can use. Instead of writing new, so we say string my string equals CS6312. Because we do string operations so often, we don't want to have to keep going equals new string and put our string literal in there. So they have made it a little bit easier to initialize strings. Now, even though we do a direct assignment here, this is going out and creating a new string object. And my string is still a reference variable because it's pointing to a string object. Now, strings are like diamonds, they're forever. What we refer to them as immutable objects. So that means when you create a string object, that object can never change. You cannot go in there and change the contents of that object. Now, I realize this may cause a question saying, what do you mean that they're immutable? When I write code, I can change a string whenever I want. So I say string my string equals CS6312, and now I say my string equals CS6312 is great. I changed it because now when I print out my string, it has CS6312 is great. What happens though, when we say my string equals CS6312, it makes a string object. Once it makes that, CS6312 is in that object, and that contents there will never change. But when I come back here and I say my string equals CS6312 is great, what that does is it makes an entirely new string object that has CS6312 is great in it. And the contents of that will never change. So every time you do a new assignment, you modify a string, it's making an entirely new string object. So what that means is string operations can be very expensive because we're going to be constantly going out and making new string objects if we are modifying them a lot. This means that there's going to be some differences when we're using strings as parameters. And if we're doing a lot of string manipulation, it can affect the efficiency of our program, because every time we manipulate that string, a new string object is going to be allocated. So let's look at a couple examples here. How many objects are created in this example? If we say string A equals CS6312, string B equals new, 2 objects are created. This is a direct assignment, but it goes out and makes a new string object. This one, of course, we have the keyword new, and so we know that makes a string object, but 2 objects are created in this particular instance. If I look at another example here, S1, this makes a one string object, this makes another string object. Now when I concatenate those together, this goes out and makes another string object. So after these 3 lines of code have been executed, 3 different string objects have been created. Now one thing we've got to take note of, as I mentioned earlier, is that be careful when we're passing strings as parameters. To note that if you modify them, we're not going to see that change reflected back, even though they're reference variables, because we're making a new object here. So this is almost like saying new again, as we had in that one grade example. Now there's another oddity with strings, is Java will attempt to say space and reuse string literals. So we got to remember here that all strings are immutable. So if we come out here and say S1 equals this string literal here, and I say S2 equals the exact same string literal, it goes out, and when I execute this S1, it makes a string object that has CS6312 as great fun in it. Because that object, 1, takes up space, but 2 can never be changed, and it wants to take advantage and save some memory space, the Java virtual machine is smart enough to figure out that these are the exact same strings. So it's going to come out here, and S1 and S2 are going to point to the exact same string object. So if I said as S1 equal S2, that's actually going to return true because S1 and S2 are pointing to the exact same object. If we ever come in here and say equals new string, when we say new, this here is actually going to go out and make a new object. So this is going to make a new object, this is going to make a new object. Even though they're the same string literal here, 2 different objects have been created because we have used the word new, which forces the instantiation of an object. Now, because working with strings and doing string manipulation can end up doing a lot of allocation in the memory and be a little bit inefficient, Java has created a string buffer class that when you use that class and you manipulate on it, it doesn't go out and make a bunch of new string objects. So it just uses a single object, and then when you manipulate that, you're manipulating that same object. This string buffer class is really truly only used for manipulation of a string because it doesn't have the nice assignment operators or the concatenation operators. You actually have to call in a dot append method, etc. to manipulate that. The last thing that I want to mention in regards to strings is a lot of times when we're working with those, we need to be able to parse a string. For example, here I have the string that's separated by spaces. The string tokenizer class is a very nice class that you can call and say, tokenize that. In other words, give me the individual tokens, in this case that are separated by spaces. It's going to return me then an array that's going to give me each individual token. So if I use the string tokenizer class and said tokenize it based on spaces, it would turn me a string array that would have Dwayne, Yoder, Carrollton, Georgia, male, married in it for each element of the array. When we're working a lot with strings and trying to write them out to a text file, a lot of times we'll hear a CSV string. That just means a comma separated variable string that our individual tokens within the string are going to be separated by commas. That gives me an indication that if I'm going to now parse the string, I know that between each comma field, it represents a different field. Again, I can use the string tokenizer class and say I need to parse it based on the commas, and it will return me an array for each individual token of that particular string. So that's the end of this particular lecture.